In a dimly lit room, rows of humming machines emit an eerie blue glow. These aren't ordinary computers, they're the vanguard of a revolution. NVIDIA's latest supercomputers are pushing the boundaries of quantum computing, and the implications are staggering. From unbreakable encryption to solving complex real-world problems, we're on the cusp of a new era. But are we truly prepared for what comes next? Let's delve in. 1. The unlikely alliance, when Nobel meets silicon. Picture this. A renowned physicist celebrated for unraveling the mysteries of complex systems shakes hands with engineers from a company best known for gaming graphics. It sounds like the setup for a joke, but it's the reality behind NVIDIA's quantum computing breakthrough. Nobel laureate Giorgio Parisi, famed for his work on spin glass theory, didn't set out to revolutionize computing. His focus was on understanding the bizarre behavior of certain materials at the quantum level. But when NVIDIA caught wind of his research, they saw an opportunity. The result? A partnership that would make even the most hardened tech skeptics raise an eyebrow. Parisi's team gained access to some of the most powerful supercomputers on the planet, while NVIDIA got a front-row seat to cutting-edge quantum theory. But here's the kicker. This unlikely alliance isn't just about academic curiosity. It's laying the groundwork for quantum computers that could solve problems our current tech can't even begin to approach. We're talking about optimizations that could revolutionize everything from drug discovery to financial modeling. Of course, not everyone is convinced. Critics argue that quantum computing has been just around the corner for decades. Are we really on the verge of a breakthrough, or is this another false dawn? 2. The GPU gambit, betting the farm on quantum. When you think of NVIDIA, you probably picture sleek graphics cards powering the latest video games. But behind the scenes, the company has been quietly pivoting. They're betting big on quantum computing, and it's a gamble that could redefine the tech landscape. In 2023, NVIDIA poured a staggering $1.2 billion into quantum research and development, more than double their investment from the previous year. Why the sudden urgency? The answer lies in a growing realization. Traditional computing is hitting a wall. Moore's law, which predicted the doubling of transistor density every 2 years, is slowing down. We're approaching the physical limits of how small we can make transistors. Quantum computing offers a way out of this impasse. Instead of relying on binary bits, quantum computers use qubits that can exist in multiple states simultaneously. This allows them to perform certain calculations exponentially faster than classical computers. But here's where NVIDIA's strategy gets interesting. They're not trying to build quantum computers from scratch. Instead, they're using their existing GPU technology to simulate quantum systems. It's a bit like using a flight simulator to design better planes. This approach has its critics. Some argue that simulating quantum systems on classical hardware will never be as effective as building actual quantum computers. But NVIDIA's defenders point out that simulation allows for rapid iteration and testing of quantum algorithms without the need for expensive specialized hardware. The truth probably lies somewhere in the middle. While simulation has its limits, it's providing valuable insights that could accelerate the development of real quantum computers. And if NVIDIA's gambit pays off, they could find themselves at the forefront of the next computing revolution. 3. The two-dimensional tango, unraveling the Ising spin glass. Let's dive into the heart of the research that's causing such a stir. At its core, we're dealing with something called the Ising spin glass model. Don't let the jargon intimidate you. This concept is simpler than it sounds, and it's key to understanding the potential of quantum computing. Imagine a flat surface covered in tiny magnets. Each magnet can point either up or down. In a normal magnet, all these little magnets would align in the same direction. But in a spin glass, it's chaos. The magnets interact in complex ways, creating a disordered system that's fiendishly difficult to predict. Why does this matter? Because many real-world problems can be mapped onto this type of system, from protein folding to optimizing supply chains. If we can understand and manipulate spin glasses, we can solve a whole host of practical issues. Here's where NVIDIA's supercomputers come in. Simulating these systems is incredibly computationally intensive. A modest-sized spin glass model can have more possible configurations than there are atoms in the universe. Classical computers struggle to handle this complexity. But quantum annalers, a specific type of quantum computer, are tailor-made for this kind of problem. They work by slowly adjusting the system until it settles into its lowest energy state, effectively solving the problem. The research team used NVIDIA's GPUs to simulate how these quantum annalers behave. They discovered something surprising. Even in a two-dimensional system, there's a sharp transition point where the behavior of the spin glass changes dramatically. This might sound abstract, but it has profound implications. It suggests that quantum annalers could be far more effective at solving certain types of problems than previously thought. We're talking about potential speedups that could turn month-long calculations into minute-long ones. But there's a catch. While the simulations are promising, they're just that, simulations. The real test will come when we can build quantum annalers large enough to tackle these problems in practice. And that's still a significant challenge. 4. The hidden cost of quantum supremacy. As excitement builds around quantum computing, it's easy to get caught up in the hype. But there's a darker side to this technological leap that we need to address: the environmental impact. Quantum computers, for all their potential, are energy hogs. The current generation of quantum processes needs to be cooled to near absolute zero. That's colder than the depths of space. This cooling process requires massive amounts of energy. Let's put this in perspective. D-Wave's 2000Q quantum annealer, one of the most advanced in the world, consumes about 25 kilowatts of power. That's roughly equivalent to the energy use of 20 average American homes. And that's just for a single machine. Now imagine scaling this up to match the processing power of our current supercomputers. The energy requirements would be staggering. Some experts estimate that a large-scale quantum computer could consume as much power as a small city. This raises a troubling question. Are we solving one problem only to exacerbate another? As we push the boundaries of computation, are we inadvertently accelerating climate change? NVIDIA's approach of using GPU simulations offers a potential middle ground. By simulating quantum systems on more energy-efficient classical hardware, we can make progress without the extreme energy costs of full quantum systems. But even this is not a perfect solution. The Leonardo facility in Bologna, which was used for this research, consumes about 10 megawatts of power at peak operation. That's enough to power several thousand homes. And this was just for the simulation work. Actual quantum computing at this scale would likely require even more energy. There's also the question of rare earth elements. Quantum computers rely heavily on these materials, which are often mined under questionable environmental and ethical conditions. As demand for quantum hardware grows, so too will the pressure on these resources. The quantum computing community is aware of these issues. Research is ongoing into more energy-efficient quantum architectures and cooling methods. 5. The quantum workforce dilemma. Are we ready? As quantum computing inches closer to practical reality, a new challenge looms on the horizon: who's going to operate these machines? The quantum workforce gap is real and it's growing. A 2023 report by the Quantum Economic Development Consortium estimated that the quantum industry will need between 50,000 and 100,000 skilled workers by 2030. Currently, we're nowhere near meeting that demand. Why the shortfall? Quantum computing sits at the intersection of multiple complex fields: physics, computer science, mathematics, and engineering. Finding individuals with expertise across all these areas is like searching for a quantum needle in a haystack. NVIDIA's research collaboration highlights this issue. The team included physicists, computer scientists, and hardware engineers. This multidisciplinary approach is becoming the norm in quantum research. But our education system isn't keeping pace. Universities are scrambling to develop quantum computing curricula, but it's a moving target. The field is evolving so rapidly that by the time a 4-year degree program is established, parts of it may already be outdated. This skills gap isn't just an academic concern. It has real-world implications. As quantum computers become more powerful, they'll be able to break many of the encryption systems that currently protect our data. We'll need a new generation of cryptographers to develop quantum-resistant security measures. There's also the question of accessibility. Quantum education is currently concentrated in a handful of top-tier universities and tech hubs. This creates a risk of exacerbating existing inequalities in the tech industry. Some companies are taking matters into their own hands. IBM, for instance, has launched a quantum education initiative aimed at high school students. NVIDIA itself offers free online courses in quantum computing basics. 6. Quantum's double-edged sword: security in the post-quantum world. As we marvel at the potential of quantum computing, a shadow looms on the horizon. The same technology that promises to revolutionize fields like drug discovery and financial modeling also poses an existential threat to our current cybersecurity infrastructure. Most of our online security relies on encryption algorithms that are extremely difficult for classical computers to crack. But quantum computers, with their ability to perform certain calculations exponentially faster, could shatter these protections like glass. This isn't just theoretical. In 2019, a team of researchers used a quantum computer to factor a 250-bit number in just 10 seconds. A classical computer would have taken years to accomplish the same task. While 250 bits is small by modern encryption standards, it's a stark warning of what's to come. The National Institute of Standards and Technology, NIST, estimates that within the next 20 years, sufficiently large quantum computers will be able to break RSA 2048, one of the most widely used encryption algorithms. This has led to a race to develop post-quantum cryptography, encryption methods that can withstand quantum attacks. NVIDIA's research into quantum annealing plays a crucial role in this arena. By simulating quantum systems, they're helping to identify potential vulnerabilities and test new quantum-resistant algorithms. But here's the catch. We need to implement these new security measures before large-scale quantum computers become a reality. It's not enough to develop quantum-resistant algorithms. We need to deploy them across our entire digital infrastructure. This is a monumental task that will require cooperation between governments, tech companies, and cybersecurity experts. The situation is further complicated by the harvest now, decrypt later threat. Nation-states and other actors are already collecting encrypted data with the intention of decrypting it once quantum computers become powerful enough. This means that sensitive information we're sending today could be compromised years down the line. On the flip side, quantum computing also offers new tools for securing data. Quantum key distribution, QKD, for instance, uses the principles of quantum mechanics to create virtually unbreakable encryption keys. However, QKD requires specialized hardware and infrastructure, which are not yet widely available. As we stand on the brink of the quantum era, we must navigate this double-edged sword with care. The same power that promises to solve some of our most pressing problems could also create unprecedented security challenges. 7. The ethical quagmire, navigating quantum's moral maze. The potential of quantum computing is vast, but so are the ethical questions it raises. As we push forward into this new frontier, we must grapple with dilemmas that have no easy answers. One of the most pressing issues is the potential for quantum computers to exacerbate existing inequalities. We've already seen how access to cutting-edge technology can create winners and losers on a global scale. Quantum computing could amplify these disparities. Wealthy nations and corporations that can afford to invest in quantum research will reap the benefits, leaving others further behind. This isn't just a hypothetical concern. In 2024, China announced a major breakthrough in quantum communication, developing a satellite-based QKD network that promises unparalleled security. This puts other nations at a significant disadvantage in terms of secure communications, leading to a new kind of digital divide. There's also the question of intellectual property. As quantum algorithms and technologies become more advanced, patent disputes are likely to become more common. Who owns the rights to a quantum algorithm developed by a machine learning system using data from thousands of researchers? It's a legal gray area that courts are ill-equipped to handle. Then there's the issue of surveillance. Quantum computing has the potential to revolutionize data analysis, allowing for the processing of vast amounts of information at unprecedented speeds. This could be a boon for everything from climate research to healthcare. But it also raises the specter of mass surveillance on a scale we've never seen. Imagine a state actor using a quantum computer to sift through the communications of millions of people in real time, identifying dissent and silencing opposition before it even has a chance to organize. Balancing these concerns requires a nuanced approach. Policymakers, tech leaders, and ethicists need to work together to establish frameworks that ensure quantum computing benefits all of humanity, not just a privileged few. This includes investing in education and training to bridge the quantum workforce gap, ensuring equitable access to quantum technologies, and developing robust ethical guidelines for their use.